Yeah. Now it's better.
Okay, now it's much better.
So yeah, I will present you my work about reachability in multi-agent transfer systems, which was a joint work with Loic, Helouet, Nathalie, Bertrand, and Engel, Lefaucheux. A little bit of motivation first. So what you can find in our model will be some number of agents that have a resource on them that carry an energy level, and there will be some quantitative constraints on this energy. And the agents will try to perform to achieve some reachability objective. And what is new in our model is this notion of transfer. Our agents will be able to perform a transfer of this energy, and this is basically what you can find, all of this, in urban transport systems with regenerative braking. So for instance, you have a train that brakes. It converts a fraction of its kinetical energy into electrical energy, and then it sends this new energy to another train that is accelerating. Okay, so I will first present you the proper model of transfer systems and the different variants that we considered. And then I will focus on a single variant, try to convince you that our result of complexity for this variant is true, and then I will have a small part of conclusion. Okay, so first, I want to, before to come to the transfer system model, I want to present it with a single agent variant first, which is way simpler because there is no transfer, there is only one agent. So what you can find here is a graph on which there is a single agent moving. There is an initial state where the agent initially is, and there is an objective state, vertex here, which the agent tries to reach. And so the agent has an energy level here, initially it's 0, and when the agent moves through an edge, it gains in energy the amount you can find on the edge. I will move the mouse up. But the energy level cannot go below 0, so you cannot go through this edge here, but you can go down and then reach your objective vertex. Okay, so this is for one agent. And now for multiple agents, so you will have the same thing as before, one graph for each agent, an initial state and an objective state. But what you will find that were not present before will be these green and red boxes, which are called transfer groups, that we call transfer groups. And when two agents are on states of the same transfer group, they can send any amount of energy from one to the other. Okay, and the other thing that we need to consider is how the agents move relatively from each other. And we considered 3 different semantics for the synchrony, so asynchronously, synchronous, and weak synchronous. And I will precise this a little bit later. So formally, what you find in our model is one graph for each agent and a set T of transfer groups, which is basically these red and green boxes here.
So you can transfer the +3 to the other guy?
Yeah, that's it. So here, suppose the agents move synchronously. They move one step, they are both in the green transfer group. This one has 3 energy units, this one has 0. Then one can send any amount, 1, 2, or 3, to the other. Okay. And our formal problem is a reachability problem. So we give a transfer system, a set of initial vertices and a set of objective vertices. And the question is there a run from a starting configuration, so 0 energy units for each agent starting in each initial vertices, that reaches a configuration in which each agent is on its objective vertex. Okay. So the 3 different semantics that we considered, asynchronous, synchronous, and weakly synchronous, I will present them using these small examples that you can find here. So first, for the asynchronous semantics, in this semantics, the agents move one by one. So for the agent to reach their objective here, you can ask the first agent to move to P1, and then it has one energy unit. A2 is still on Q0. It can send the one energy unit to A2, and then A2 has one to pay for this edge here. And A1 can also reach its objective, and you have this run that represents what I just explained. In synchronous semantics, however, this configuration, starting configuration, is a deadlock because in synchronous semantics, the agents must move together, and here agent 2 cannot move from Q0 to Q1 because it doesn't have the one energy unit needed. And finally, there is the weakly synchronous semantics, in which, once again, we require the agent to move together, except if the agents do not have any possible move to fire, any edge to fire. So for instance, this is the case for agent 2 here. There is no possible move for this agent. So A1 moves alone first, then it can send via this transfer transition the one energy unit to the agent 2, and then they reach their objective state together. Okay. And so along the different semantics, we also consider different types of transfer modes. The first is transfer by groups that I already presented. This is a basic case. We have potentially several transfer groups. And the second transfer mode is global transfer, in which you have a single big transfer group which covers every vertices of the system. And in this second mode of transfer, every transfer is always available among any pair of agents, any pair of vertices. So virtually, you can think of it as the agents share a big common energy level. Okay, and so this is the same example here and there, except that here we consider global transfer. And with this instance here, we have the interesting following fact. It's a negative instance for synchronous semantics and transfer by groups, but it's positive when you come to global transfer, and then it's always positive with asynchronous semantics. And this justifies that these problems, these different combinations of transfer modes and semantics are different problems, and so that's why we studied them separately. So maybe a little bit of explanation. With asynchronous semantics, why is this a positive instance? So here, what you can notice is agent 1, the first agent, has a positive loop here, but it has a starting cost of -1. So agent 1 needs to meet the agent 2 in the green transfer group. Agent 2 sends one energy unit to the agent 1, and then it can start to take his loop, accumulate as much energy as it wants, and then give this energy through the red transfer group here, and both agents are happy. This run that I just described is also possible with global transfer because it's just less restrictive. Okay, so this is positive and this is positive, but this with synchronous moves and transfer by group is negative. So here, agents must move together, but for agent 2 to pay the -100 here, agent 1 must have accumulated enough energy and then give it through the red transfer group. But to do that, they must spend as many move transitions between the green transfer group and the red transfer group. However, you can notice here that agent 2 has at most 3 energy units between the two groups, transfer groups, And so it has at most 3 move steps to wait between the 2 transfer groups. This is not enough for agent 1 to accumulate the 100. But in global transfer, when they reach the middle, their middle vertex here, you can notice that every 2 steps, there is globally 1 energy unit that is gained. So here, -1 + 4 is +3, and here -1 - 1 is -2, so globally +1. The system, the whole system, enters the 2 steps loops that accumulates energy, and then everybody can be happy ultimately. Okay. So here are condensed version of the different results we came up with in the paper. This is all the complexity results that we found combining different semantics and transfer modes. And that you can see is it's pretty interesting that it ranges from NP-hard to undecidable. However, there are some complexity gaps here and here that we hope to close one day. And so the variant that I will focus on is transfer by groups and asynchronous semantics. So here, transfer by groups, you have the local boxes, not a big one, and move asynchronously. Agents move one by one. Something that I want to emphasize on this small instance here that will be helpful just right after is that in this example that you can notice that what you can view, what you can imagine is that agent 1 helps agent 2 to reach its objective. And this notion of helping will be useful to prove the PSPACE membership of this instance, of this variant of the problem. Okay, so to prove PSPACE completeness, we first prove PSPACE membership and then hardness. How did we prove PSPACE membership? So we obtained an exponential bound of the energy levels of the agents. This means that the energy level never needs to go above this exponential bound. Where does this bound come from? So suppose that agent 1 has enough energy to do anything that it may have to do. And by may have to do, I think of helping every other agent of the system. So here, helping is a more generalized notion that I presented previously, because it might be helping indirectly via another agent or many other agents. So here, agent 1 sends some energy, has to send some energy to agent 2, and then agent 2 in turn helps agent 5 and agent 6. So agent 1 needs to provide for agent 2 to help agent 5 and agent 6, and then reach its own objective. And the thing is, if you have enough energy to do anything, these red arrows here, it means reaching, trying to meet the other agent in a transfer group, and the green arrow reaching your own objective state. So accomplishing these arrows, if you have enough energy, you can say, okay, I don't care for the negative cost, and I move straight to the point, just as a simple path. And so here what you have is that if you have enough energy level, every arrows you can find on this graphic can be done using a simple path on the graph. And this is helpful to bound the energy that this simple path costs, and so that the energy that agent 1 needs to provide to help every other agent of the system. So we take B to be the highest cost of a simple path of the whole system. And this is, so because we encode the weights in binary, this bound B is exponential on the biggest weight, and so exponential in the transfer system. Okay, so Now the question is, how many arrows are there on the system? How many times do I have to pay the B at most? And obviously there is one green arrow for each agent, because each agent needs to reach each objective. And there is one red arrow for each agent, except the first agent, agent 1. So this is n plus n minus 1 to n minus 1 if you have n agents times b. And this is an exponential bound. So now you know that you can store configuration in sorry. You know that to store a configuration you need at most exponential weights. So in binary, at most polynomial space to store these weights. And so you have a non-deterministic p-space algorithm, and with Savage theorem you have a p-space algorithm that solves this problem. Okay, so this was membership. And now, what about hardness? So to prove that this problem is p-space hard, we reduced the reachability in safe Petri nets to our reachability problem with asynchronous semantics and transfer by groups. What is safe Petri nets? So it's the same thing as Petri nets, but you can never have more than one token in each place. Okay, so this reachability problem is known to be p-space complete, and this is why we reduced it to. So this is why we have the p-space hardness. The first thing that I want to make you notice here is that in our reduction there is one agent for each places of the Petri net. So here I have place 1, 2, and 3. There is just a very small safe Petri net. I have 3 agents, 3 places, and so 3 agents. And I have some states that we'll call stable states for each agent. One that is labeled by 0 and one that is labeled by 1, that represents the amount of token there is in the corresponding place. So here, to encode the marking M, you have agent 1 on the stable state 1, agent 2 on the stable state 0, and agent 3 on the stable state 1. And now, the second thing we need to have in our reduction is a way to simulate the firing of a transition in the safe Petri net. And to do that, we added a new agent that we call the controller, and that will, between each stable configuration, choose a transition to fire. And when the controller chooses the transition to fire, it will take a path, and there are corresponding transfer groups that are linked to that path and to that transition. So here, if the agents want to follow the agent need to follow the choices of the controller, because it's the only one that can provide for the 1 energy unit that it has to pay, etc. And so there are a little bit more details than that to accomplish the proof. Mainly, why do we need the 2 phases? But I will not enter in these details right now. The idea is that the controller chooses the transition, and all the agents need to follow the choice of the controller, and everything goes according to plan. We have simulated the right transition, for instance here. So agent 1 goes from the state 1 to the state 0. Yeah. Agent 2 from the state 0 to the state 1, and agent 3 from the state 1 to the state 1. And you can enforce the system like that to follow the constraints of the transition. And so we obtain p-space hardness and p-space completeness of this variant of the problem. And what about the remaining boxes of this table? So the first thing to complete the filling of this table that we can notice is that there are some simple reductions that we can make among the different variants of this problem. So the first is between, so you can reduce global transfer to transfer by groups, because global transfer is just transfer by groups with a single transfer group. You can reduce asynchronous semantics to synchronous semantics, because when you add +0 loops on the vertices, you can simulate the weighting of the agent and the asynchronous moves. So you may always have one agent moving while the other waits. And you can reduce synchronous semantics to weakly synchronous semantics, because remember, so weakly synchronous semantics is the same as synchronous, except that you allow the agent to wait if they have no possible move to play. But here we add from each vertex an edge that goes to a bad state that leads to nothing. That costs 0, so it is always available, and the agents may never wait because they always have at least one move available that they must take, if possible. So it is not allowed in this reduction for the agent to reach the objective to wait on the states, so it means to reach the bad state. And with these three little, so here with only two little, with this result and this result, we can obtain that this variant is in p-space and that this variant is p-space hard. Then to obtain the NP hardness of this variant, so global transfer and asynchronous semantics, we obtain a reduction from subset sum. And to show that this is in EXPSPACE, we reduced the reachability of this variant to vast cover. Here, so we have p-space completeness of these two variants of the problem. We only needed to show that this one is in p-space and this one is p-space hard, because with this reduction, the third result I presented earlier, we obtain the completeness of the whole box, the two boxes. And we, once again, use the polynomial bound on the energy level trick to obtain the membership and reachability from, and we reduce, and there is a reduction from safe Petri-net reachability. Okay, and then more surprisingly, so the undecidable box, we obtained a reduction from the Minsky machine termination problem to weakly synchronous and transfer by groups. Okay, and as a conclusion, so we propose a new model to represent multi-agent system in which agents may perform some form of transfer. We obtain a wide variety of decidability / complexity results with different semantics and transfer modes. And these results range from NP hard to undecidable. Okay. And so for future works, the first thing that we want to do is close the complexity gaps that are still in the table. Ongoing works here, we raise the question of what if all agents are playing on a copy of the same graph. So here it's a parameterized question. And finally, also an ongoing work, what happens when we lose collaborative agents and consider that they play against each other. So it's about finding good Nash equilibria or subgame perfect equilibria. Thank you.
thanks again, Luca, for the talk. Are there, I think we have a few minutes, 2 minutes more precisely, 3 minutes. Are there any questions? No? I have one, at least one question to start, just maybe to get the thing started. I was wondering why you can't just, I mean, maybe can you give the intuition why you cannot just convert the last case, the undesirable that you mentioned, undesirable, to just Petri-net reachability? What's the problem with that? Why you can't encode the zero test?
The thing is, with weakly synchronous semantics, there is something that can happen that you cannot. Oh, you went too far. Sorry. Yeah, there is something that may happen that cannot happen anywhere else. Is that you can punish the agents for having too much energy, because then you can force them to move through an edge.
Okay. Yes,
okay.
Yes.
However, sometimes they maybe prefer to wait. So suppose here there is a -1 that leads to a bad state and a -2 that leads to good ending. The agent prefers to wait for another agent to send him energy than having one energy and going to the bad state.
So because you can wait for a really long time, I guess, in this case?
Yeah, maybe. Yeah. And so the zero test comes from here. You can test if the energy has at least one energy unit or not.
Right, okay. How do you connect this to the problem that you mentioned at the beginning? Because here you have some kind of reachability. Well, I guess you want to make sure that it's a specific, I mean, if you look at the original problem that you mentioned, like the collision stuff, it's more like...
here?
Yeah. So is this is also like control state reachability, or is actually maybe reaching something with specific energy, something bigger than
so
something
here a question that you may ask yourself is, if I have an infinite run, what would be the best ratio of energy that I can transfer by move transition? We didn't elaborate about around ratio questions in our transfer system model, but it could be interesting. However, it may be more relevant if we had continuous numbers, so timed automata, I don't know. But you can consider, okay, my network, my transport network must accomplish a daily routine of each train moves along this whole trip and then reaches the end station. So this can be seen as reachability if you consider only finite runs. But then the question again is, what is the best amount of energy can I transfer along these runs? However, these are threshold questions. Maybe they are linked to threshold questions, and which are the.
Then you get essentially the problem that you're considering.
That's it.
Yeah, got it. Right. I think we kind of ran out of time. So yeah, thank you, Luca, again for the talk.